Swayam Prabha. Digital India. Educated India.
Welcome to Module 8, Lecture 5. This is the last lecture of this module, and we will continue with durability of concrete. In this last lecture, we will look at general strategy. Of course, some issues related to rebar corrosion would surely be looking into. So, first we will look into some of the empirical models which are available for corrosion, and then role of concrete and concrete quality and durability, general strategy of achieving durable concrete. So, in case of corrosion, the propagation period we talked of in the service life, we talked of, if you recall, we talked of service life. There are two phase. The simplest model, there is a depassivation or initiation phase followed by a propagation period. So, today we are talking of this, this is related to carbonation and all that. So, we are now looking at propagation period, which actually is governed by the rate of corrosion, of course, which is function of environment, etcetera, which you have seen earlier. So, some fundamentals we did look earlier, but the result of corrosion could be loss of steel cross section. In some cases, I said especially in the case of pitting, in case of pitting it is loss of steel cross section. A second case could be delamination of the rebar, that is, this is your reinforcement bar and the surrounding concrete is here, surrounding concrete is here, surrounding concrete is here. Now, let us say this is the bottom side and there is a delamination from the rebar. So, this actually gets separated out, bar gets separated out at the bond is lost and it gets delaminated. So, that could be a second sort of scenario, and the third scenario is cracking of cover concrete. So, this is most concrete, is quite common, although delamination occurs in case of slab. There could be cracks of this form as we have seen earlier, cracks of this form, and then there could be delamination of the cover. If this is the cover, this is the cover, and this might fall off completely. So, this could be three different cases, and let us see what are the empirical models, some empirical model available for this. So, case A, loss of steel cross section. In that case, this is the rate, this is rate actually, and this is the maximum cross section loss allowed. Delta R max is the maximum loss of cross section allowed, right, cross section allowed, loss of cross section allowed, because after that what will happen, if the material is lost significantly, then it may not be able to carry the load. So, maximum loss allowed is, it will be related to maximum loss allowed. So, rate of propagation, DR is the maximum permissible loss of cross section. So, if I know rate in some manner and maximum loss, then it is possible, but then rate must be expressed in terms of depth of penetration, which I said 3.27 etcetera, a formula which we looked into in the last class. All right. So, this is one way. Case B is case B was related to delamination, and in this delamination the rate can be related to C T into R 0. In fact, this is empirical. So, it can be, this rate can be found out from any, this rate can be found out for any case, all of the three cases, and C T is a factor for temperature. We will look into this. So, what are the values of C T? R 0 is you can say reference corrosion rate. So, at standard temperature and at any other temperature this will be given by R, and this is the time of corrosion would be 80 C by dr, where d is the bar diameter and C is the cover depth. So, it is delamination, time, right, and that is 80 C by dr, where C is the cover depth, D is the bar diameter. So, it is proportional to C by D, R is the rate of corrosion, and same earlier also we had rate of corrosion. So, its rate of corrosion is same expressed in terms of depth of penetration. So, these are actually this, if you see this is covered by bar diameter, and this is rate of again millimeter or mils per year, I mean it will be micrometer per year or whatever it is. So, Tc you will get in terms of time, Tc of course, you will get in time. So, ATD, this is an empirical equation. So, C is the cover depth, D is the bar diameter, Ct is the temperature coefficient, and this is valid for all three models that the empirically those people who have derived, they have given this table for Ct. R0 is rate of corrosion at 20 degree centigrade, and again given in a table. So, therefore, for the kind of condition where actually experiments were done, where this empirical model is applicable, there you can use this formulae and first find out the R0 which is given for the table, given in the table. Then if there is a temperature change, rate you can determine from this, and Tc is the time for delamination given by this model. This is from this available in a book by Sarja and Vasakari, durability design of concrete, durability design of concrete. So, 20 degree tables I have just reproduced some of the part of the table is given if depending upon the relative humidity, high humidity this value is low in carbonated concrete, in chloride concrete. So, R value R0 value for chloride concrete and carbonated concrete. Now, this is a relative humidity, this is 85, this value is fairly high in micrometer per year when relative humidity is 95%. It is carbonation has already occurred, carbonated concrete, this is the guidelines given for the corrosion. Now, you see if the relative humidity becomes very low, corrosion rate becomes small, because corrosion requires presence of moisture as well. But while in chloride still this continues, and maximum is again around 95% relative humidity. So, 100% relative humidity within the concrete pore or in the condition that has been considered, it actually reduces down. So, with the relative humidity R0 values can be obtained at 20 degree centigrade, and Ct values one can obtain, for different locations they have given. For example, northern Finland very cold, very cold. So, they have given Ct coefficient 0.21, because it will be less than 20 degree centigrade, and Madrid which is close to 20 degree, Amsterdam there this is 3 and Amsterdam 12. So, the temperature where it is depending upon the temperature these values are changing in case of sheltered or in case of exposed to rain. See, sheltered from rain, this is the scenario, exposed rain. So, these are empirical relationship, but it gives you a kind of guideline or understanding sort of. What we understand from this is there could be three cases possible. One is delamination, another is loss of the diameter, and third is cracking of the cover concrete. There are three situations possible, and all are dependent on R, rate of corrosion, which again is a function of temperature and also chloride or carbonated concrete, relative humidity. So, it varies with all that, and varies whether it is exposed to rain or sheltered from rain, and Ct values are given here. So, this is a function of temperature. So, case C, then the last one, the cracking of cover concrete, this is given as d minus d mean divided by 2r, Tc is d r max, that is we have seen earlier. Now, d is the bar diameter and average corrosion rate for both cracked and uncracked concrete. So, this is for uncracked concrete, this is for cracked concrete, d minus d minimum, right, divided by 2r, where average corrosion rate for both cracked and uncracked concrete. So, Tc this is given, right, for different relative humidity carbonated concrete, the this relative humidity carbonated concrete, these rates are given, this is less than 2, and d is the bar diameter, actually the minimum d that is likely to be there, because R max is known. So, this divided by 2r, that will give you the time required for cracking of the cover concrete. So, these three empirical equations are given, but let us understand average corrosion rate in both cracked and uncracked concrete for relative humidity, chloride contaminated concrete, these values are given, average corrosion rate. So, this is also given, in terms of average corrosion rate in carbonated concrete, sorry, this is for chloride, this for carbonated situation, average corrosion rate is given here, average corrosion rate is given here, and time is given by this formula, where R you can determine from this. For carbonated concrete, for 2 cases it is shown, for other cases these values are available. So, some guidelines actually it gives you, right, and this is in the chloride situation, average corrosion rates are given for different relative humidities to be used in this formula for cracked concrete, the concrete which is already cracked, right. Now, basically cracking of cover concrete is an important issue, and it can be modeled. Earlier it was modeled considering thick and thin cylinder situation, or by FEM modeling currently people are trying. The properties which are important is modulus of elasticity, cover depth, tensile strength, bar diameter, C by D ratio, rate of corrosion in terms of penetration and density of rust. So, all these properties are required if you want to predict the time of cover concrete cracking. That is much relatively more sophisticated than what we just talked about. These were empirical models, while this what I am talking of right now is empirical, but based on theory of elasticity, mechanical model of cracking of the cover concrete. So, if you want to estimate cracking cover, this is how one can model them. Now, the phenomena is looked upon like this. This is your concrete and this is the rebar. So, the corrosion has occurred here, the corrosion has occurred here, the corrosion has occurred here, red colored shows corrosion product has formed. Now, this will exert a kind of pressure. So, this kind of exert a kind of pressure. So, those people who use cylinder theories, they assume this is your cylinder, but otherwise continuum you can consider, and the pressure that will be exerted outside, that will cause excess strain in this zone, strain as well as stresses in the zone, and one can solve the problem of elasticity and find out the time or cracking of cover concrete. But a lot of work needs to be done here. There have been attempt verification of the models by experimental work is not easy, but thick cylinder could be assumed to be like this, thick cylinder scenario large, and thin cylinder is with this, the pressure is from inside. So, the pressure is from inside, there is a pressure. So, you can consider this thickness being very small if it is a thin cylinder consideration and apply those models. But one can actually do finite element modeling for the complete thing and then arrive at time, but there has been a lot of uncertainties involved in such modeling, material properties, how much, what is the kind of interfacial properties of the interface, the porosity in the interface between the steel bar and the concrete, because some rust product will go and get accumulated there. So, pressure may not increase. Also, the properties of the rust product, their modulus of elasticity, and several other situations, whether you take it as a what kind of problem you take it, plane strain problem, and then you take the uniform pressure, bearing pressure becomes very difficult. So, you take uniform pressure in the surrounding system, or take uniform strain in the deformation. So, all these are, there are complexities involved in this modeling, but this is how one can visualize this, what happens, and this can result in the cracking of cover concrete, which is defined as a service line. So, these are the further more sophisticated theoretical modeling. At the moment, even those empirical models that I talked about earlier would be applicable to only those specific conditions, but this gives us some understanding at least that on what factors does this propagation period depends. So, what we see right now is the propagation period will actually depend on the environment, relative humidity, chloride contaminated concrete or carbonated concrete. So, chloride concrete or carbonated concrete, and what is more important, loss of bar diameter or cracking of the cover concrete. Whether the concrete is already cracked, then situation will be different. So, all these factors that we have understood from our last couple of slides or last discussion that has gone on. So, with this I think we can close our discussion on corrosion propagation models, can look into strategy for durability, and that is what we will look into. Now, strategy for durability, that has been, so we have understood all the problems, deterioration process, and their details in last 4 lectures and the part of this lectures as well. So, what is the strategy? Currently what we have understood is our understanding in terms of the physical, the phenomena and physical models for deterioration is really limited, very limited. Possibly carbonation is a function of under root time, T time, this is experimentally validated. Many things would not have been experimentally validated, many things would not be experimentally, couldn't be experimentally validated because of the long term required. Accelerated tests quite often may not actually represent the real situations. So, but we have to have strategy for durability, and we had already in place over the years, which is improving. Good lot of it is actually right now prescriptive. So, we will look into the prescriptive situation of IS code, but let us see what are the possible strategies, and we have got to understand, we got an understanding of the difficulties associated with doing mathematically or quantitatively estimating the service life of concrete, because it is dependent on so many factors, environment, the materials, etc., and also our lack of understanding in a complex material like concrete, which is not a single compound, many compounds, how it will react, which compound will react under what situation, all these complexities are there. Therefore, at the moment prediction of service life is practically not even in nascent stage, I will say it is in embryo stage, because your mathematical understanding is relatively very limited. So, we can't stoichiometry of the reaction and the product formation and the mechanics of till it cracks or something of that kind. That is really at its less than infancy stage, embryo stage if I may put in. So, but research are on, it will improve, but at the moment you got to have some strategy. So, therefore, let us look at the strategy. Durable concrete exhibits desired performance in exposure during service, that is what we said in the beginning. Durable concrete must exhibit desired performance in exposure during service, and all the deterioration process that we have discussed, actually we have seen that they involve ingress of water or oxygen or carbon dioxide or chloride or something agent causing degradation. So, therefore, since we can't address specific degradation phenomena, what people have done earlier, permeability has been considered. This idea is actually borrowed from the soil, because permeability of the soil is well established, its application has been well established. But one difference with the soil and the concrete would be, permeability governs the flow through the soil. Now, flow through the soil could be quite often when we are dealing with a geotechnical problem or otherwise, or trying to look at their permeability, it is quite often it could be saturated situation, many a time it will be saturated situation. So, therefore, this idea was already available for the soil, this was borrowed here, but for concrete remains most of the time unsaturated is, saturated concrete is only is a rare thing, it is not very often when we are looking, because our concrete will be exposed to atmosphere, many other cases to wetting and dryings, plus zone of marine environment, wave will come and hit. So, this one may not be able to assume it fully saturated all the time in all the places. So, but however, since the tool was already, concept was already available in soil, that was borrowed from the soil early on, because permeability is the property through which governs the flow of fluid or gases through this through porous material. So, this is the measure, permeability is a measure of ease with which liquid or gases can travel through the concrete, and is used as a qualitative measure of durability, has been used and still used as a qualitative measure of durability. I said qualitative because it can't give you any quantitative information with regards to concrete service life or anything, but you can relatively compare to concrete. More permeable concrete will be less durable than a less permeable concrete, okay. But there are other issues, we will come to them soon. So, rate of flow per unit area under steady state condition is defined as the is defined as the rate of flow under steady state condition is defined as the it is for unit hydraulic gradient, we call it permeability. So, K is the, this should be small d, this should be small d, this should be small d, d dx, this is dH dx, dH dx is a hydraulic gradient. So, the flow takes place because there is a hydraulic gradient existing. That means, if this is my specimen, there is a head here, delta H is a head here, delta H is a here, or dH is a head, and this is the x thickness. So, if I maintain, if it is saturated and this dH dx is constant, under this the flow through this one q is proportional to dH dx, like any other flow, heat flow and similar equations. This is Darcy's equation, q is equals to k dH dx, and this is coefficient of permeability. So, permeability is defined as that property which governs basically flow. It is something analogic to thermal conductivity or conductivity of conductivity, thermal conductivity or similar one. So, basically, or diffusion coefficient that we talked about in case of steady condition. So, this is coefficient of permeability. Therefore, for a given hydraulic gradient, flow is proportional to k. So, more k means more flow, less k means less flow. Now, it has been observed that k is a function of capillary porosity. So, as your capillary porosity, this is about 30%, 20%, this is about 30%, 20%, 30%, 20%, 10%, and this is coefficient of permeability 10 to the power minus 12, 13, large value 10 to the power minus 12 or so. So, this, if the capillary porosity increases, suddenly there is a percolation threshold above which it increases significantly. Below this, these values are small, suddenly from this point it starts increasing. Now, why such a thing happen? Well, when the capillary porosity is large, I mean the interconnectivity pores are important. But anyway, before I come to this, therefore, since capillary is related to capillary porosity in this manner, it should be related to water cement ratio in this manner as well. So, in the water cement ratio, if this is water to cement ratio 0.5 here, 0.6 here, 0.4 here, and it increases, suddenly it increases. So, it is a function of water cement ratio. As the water cement ratio increases beyond 0.5, suddenly it starts increasing, exponentially increases. The reason being basically earlier capillary porosity being, if it is high, supposing this is my material and these are my capillary pores are here. Now, if I have low porosity, they will be isolated. When the porosities are high, they are likely to be all interconnected. So, flow through interconnected system is likely to be more. So, they will be interconnected at high porosity, capillary porosity oblique water cement ratio, pores becomes interconnected, pores are interconnected. So, therefore, their permeability increases. So, there is a percolation threshold something like 0.5, after which all pores tends to be connected, and there is a tendency for permeability to increase. So, you can see the porosity and interconnectivity of those pores. This is an important issue as regard to permeability. It reduces with the age. As your age in days reduces, permeability, coefficient of permeability reduces. Here 10 to the power minus 6 log scale, this is plotted in log scale, but with higher the it reduces. So, 10 to the power minus 12. So, it is 10 to the power minus 6. So, all it goes to 10 to the power minus 12 in meter per second. So, with age it reduces, and we can understand hydration will progress, capillaries will get segmented, capillaries which are interconnected. So, this is our, if you recall, this is our cement particle, this is our cement particle, and this is the hydrated cement, this is the hydrated cement around, and if you more hydrated cement around, and this was the water originally, this was the water filled space. As the hydration progresses, this would go and reach there, capillary will get segmented, and we talked of capillary segmentation earlier. Therefore, interconnectivity will get reduced. So, this is related to more hydration, capillary gets, first total capillary will reduce and segmentation will increase, they will be less interconnected, therefore, permeability tends to reduce. So, what we have seen so far, permeability is a function of porosity, water cement ratio obviously, capillary porosity, and with the age it reduces, it is also function of age because of the segmentation. This we can understand from this diagram. For example, consider this one. This is the pores are all interconnected. Pores are all interconnected. Pores are all interconnected through these ones. They are all interconnected through these ones. Interconnected through this one. These are interconnected. You know, capillary pores are all interconnected. These are your capillary pores. They are interconnected. So, this if I have low porosity system, you know, that is low permeability system, they are disconnected. There is no interconnection between these two now. These interconnections are lost. So, therefore, this will be a low permeability system compared to this one which is a high permeability system. So, compared to this one, this is high permeability system, this will be low permeability system, this will be a low permeability system. So, this is low permeability system. So, you can see capillaries there, the segmented capillaries and unsegmented capillaries. Therefore, the curing must also play a role, because if you do not do the curing, capillaries will not be segmented. I mentioned this when we are talking of curing. So, capillaries will not be segmented if we do not do the minimum curing has to be done related to capillary segmentation. So, this gives us certain understanding related to permeability. So, what we have seen so far? We have seen that the permeability depends upon porosity, pore sizes, shape, interconnectivity, and this all governs the ingress of fluid through the concrete. All right. So, if we want to control the permeability, we will have to actually look into these issues. Now, porosity and pore properties are directly related to water cement ratio, that is what also we have seen, and curing also plays an important role, because it causes segmentation. So, therefore, we control water cement ratio and curing, these are very important issues with regard to strategy for durability. All right. So, interconnectivity also relates, is also related to curing, that is segmentation. So, let us see something more related to this permeability. Well, a mathematical relationship can be of this kind for permeability related to pore sizes. My idea is to show you what are the kind of properties of the system that will govern the permeability of let us say cement paste system. Now, in this one, K stands for permeability, K stands for permeability, here K stands for permeability, right. K stands for permeability, rho is the this equation is theoretically derived based on results of intrusion porosimetry, whereby interconnected pores one can determine the porosities. So, it depends upon density of water, this is acceleration due to gravity, P is the porosity, P is the porosity. This is what is called mean distribution radius or median pore. M is a factor exponent which is 2.67 for OPC paste, might vary from material to material, and D is the dispersion of the pores. That is, if I plot log of, if I plot pore size distribution, volume of pores let us say, and if I plot log of pore size, then I will get this sort of a relationship. So, this dispersion of pores, the minimum size to the maximum size, minimum to maximum size of pore. So, that D is related to that. So, D is related to dispersion of pores, D is related to pore dispersion, right. So, this is mean distribution radius, D is related to pore dispersion, rho is density of water, this is dispersion, as I said, this is dispersion, and this is J going from 1 to n, that means there are several pore sizes which you can divide into number of groups, say n groups, number of number of groups, n groups you can devise, you can divide them into n groups, and each group delta lnr gives you the small dr values, or r1 r2 minus r1. So, in log terms, so ln r2 minus ln r1, that is delta lnr, m is the exponent I already said, D is the dispersion, Rj is the jth pore size, average jth pore, and this is for any pore size. So, Rj stands for jth pore size. So, AC stands for aspect ratio of the pore, which you can take it depending upon type of pore, shape of the pore. For example, aspect ratio, if it is cylindrical, would be 1, because pore size will be circular, cross section of the pore. So, it is the aspect ratio of the cross section of the pore. For elliptic pores, this will depend upon the major axis, minor axis of the ellipse. This is tortuosity of the pores. So, this can be determined for some of the materials, some are available, but I am not interested in how to determine estimate K from all these factors right now. Mu is the viscosity of water. Now, this can be determined from Power's model, as we have seen earlier. R.5 and D, we said that it can be, because porosity can be related to, this can be also related to water cement ratio, this can also be related to water cement ratio, right, and particle size of the cement particle, size of the cement particle, water cement ratio, age, degree of hydration, that is age, all this, the D and R.5 can be related to those, and we have shown some relationship earlier when we are talking of strength, but one can relate to this. So, in nutshell, what we see? We see that K depends upon pore size distribution. As many number of size you have, K will vary according to that. So, also depends upon dispersion of these pores and mean radius. Now, all this and P itself depends on water cement ratio, average particle size of cement or particle size distribution of the cement even maybe, and age. Then it depends upon tortuosity, which also can be related to the material, the kind of age, etc., viscosity of water, and so on and so forth, and aspect ratio of pores, which in the simplest case can be 1 for circle. So, these are the factors on which permeability depends on them, but you see experimental determination of steady state permeability is difficult and time consuming. In fact, unsteady state it will vary with the degree of saturation. So, K in unsaturated state can be a function of theta, where theta is degree of saturation, or relative moisture content, So, this will, but then K generally we determine for saturated condition. So, to achieve the saturated condition steady state situation, it takes very long time in concrete, because permeability is very low. So, it is difficult and time consuming, very long time it takes, and it is not easy to do. So, this is one thing. Second aspect with permeability is permeability cannot be used for modeling moisture profile or amount of carbon dioxide that will penetrate or oxygen that will penetrate. So, oxygen permeability or carbon dioxide permeability, they are all related to saturated condition. In fact, unsaturated situation will be more it is easy to model through diffusivity. So, diffusion properties are diffusivity, although they are not necessarily diffusion as we understood from Fick's law, that is concentration dependent diffusion, but they are concentration diffusion, which is a function of the concentration because of the concentration gradient. But here the diffusion of oxygen, carbon dioxide, all this, they will be concentration dependent, but water diffusion or hydraulic diffusivity, it's it's not exactly diffusion, but it flows under capillary suction or under vapor pressure gradient. So, for water situation, hydraulic diffusivity one can use, and the equation that governs this liquid water flow or similar equation governs even vapor flow is called Richards equation, right. D theta is a function of the degree of saturation itself. This comes from extended Darcy's law. I am trying to tell you only the importance of this one here rather than permeability. If you want to find out numerically model the flow or ingress into moisture ingress into material concrete. So, these hydraulic diffusivity, theta is relative moisture content. So, you see diffusion properties are important. Similarly, carbon dioxide, this is diffusivity of this hydraulic diffusivity can be expressed in the similar manner from pore size distribution using this equation. All the things are same, except that here this is the surface tension property, This is surface tension property, then this is surface tension properties of water, and F1 relates to aspect ratio actually. This relates to aspect ratio. F1 is another property which is related is another related to a pore size distribution. All right. dV/dr is the rate of change of pore volume with radius, and tortuosity, viscosity, R.5, Rj, etc., porosity, all this comes into picture. M, which was there in exponent, that will come. So, in fact, hydraulic diffusivity can be also expressed in the similar manner from pore size distribution. Beta is a contact angle of water, which will be 1 for most of the cases, cos beta will be 1, beta is 0. So, cos beta will be equals to 1. So, one can actually relate these properties to pore size distribution. Similarly, carbon dioxide diffusion and the modeling of carbon dioxide flow can be through diffusion properties. For example, this is porosity, this is the water filled space or water content, carbon dioxide concentration and diffusion of carbon dioxide diffusion coefficient. This is the sink, that is all alkali content related to the alkali content of the concrete. So, where P is the porosity, W is the volumetric water content, carbon dioxide is the carbon dioxide concentration, D is the diffusion coefficient. This is a sink term dealing with reaction of carbon dioxide with alkaline material in concrete. Oxygen diffusion is also important. So, what we see, if we want to actually model this flow or profile within the material, how much carbon dioxide, how does the carbon dioxide concentration varies with time and space within concrete, then I got to solve this kind of equation, and diffusion coefficient, corresponding carbon dioxide diffusion coefficient will be important. We have seen the chloride diffusion equation generalized last sometime in third lecture, for second or third or fourth lecture, in fact third lecture we looked into in this one. So, what we see is the diffusion properties are important if you are trying to model them. Permeability can only give you qualitative information, a better concrete and poor concrete. But there are a lot of work to be done here, research is to be done here in order that one can actually use them for practical purposes. The equations, the material properties, solving them may not be a big problem with the kind of numerical methods and computers that is available today, but not easy to find out the coefficients in the equation. So, that is it. Similarly, oxygen diffusion is important if you are trying to model, let us say corrosion process, but corrosion there are much more complexity if one wants to model for rate of corrosion. There will be so many equations involving so many diffusion process, so many processes, also charge balance will be there. So, these are the complications involved in modeling and predicting service life. However, we can compare, and sometimes we might have to judge performance of materials in situ. So, certain permeation properties and permeability measurement is difficult. In situ it will be even more difficult. So, certain tests have been devised, namely sorptivity is a property, initial surface absorption test, sorptivity for lab specimen, laboratory specimen. This can be done in situ, fixed air and water permeability in situ as well as in the lab both, then also laboratory. BS absorption test, take a core specimen and do a absorption test. Now, this all gives us what is called permeation properties, autoclamp, and there are many more. There are a number of them, a series of them have been developed at different places, like this is in Belfast, this is BS absorption test, this is also a BS test, sorptivity originally by Hall and etc. So, there are several other properties. There is one in the Switzerland, some modification of this one, because this requires vacuum application. So, without the vacuum application. So, there are several of them which are there, and some of them can be used in situ, not on the lab specimen. So, that you can find out the performance of durability performance of concrete in structure. So, permeability is difficult to determine, but these ones will be relatively easier. But with this one you can actually compare two different concrete, but cannot predict really much, not they are not predictive, but it can tell you about which is better concrete, which is poor concrete. Anyway, this is the situation, but one more important issue is for durability cover concrete is most important, because ingress takes place through surface. So, permeability or permeation property of the cover concrete is important, and all in situ measurement of course looks into the cover measurement in cover, because that is what is approachable. But you see the stresses are maximum at the surface and rebars are placed also below the cover. So, importance of cover concrete is very important. Cover concrete is generally poor quality due to bleeding, wall effect, etc., etc. Let us look at it, this cover concrete. You see, if this is your concrete, this will be the zone of poor concrete. Why? Because wall effect, packing of aggregates are not very good here, wall effect, remember wall effect, and this could actually result in more porosity here. So, this concrete here is not very good. Water has a tendency to go up, So, maximum water ratio, maximum bleeding would occur here. Even when you do vibration, water has a tendency to come here, So, therefore, this zone of poor concrete, and water cement ratio maximum here, minimum here. Cement will tendency, cement comes down, cement has a tendency to come down, water has a tendency to go up. So, C comes down, H goes up, maximum water cement ratio, minimum water cement ratio. So, therefore, what will happen? You will have poorest concrete right up there, because maximum water cement ratio there. There will be evaporation, shrinkage and all those effects. So, therefore, zone of good concrete is somewhere here, zone of good concrete is somewhere here, and zone of poor concrete is there, and poorest concrete is there. But this is the most stressed areas, these are the most stressed areas, because flexural stresses are maximum here, depending upon of course, the kind of structure you have. Flexural compression is maximum here, tensile is maximum here. So, tensile cracking will anyway occur, torsion is maximum at the periphery, stresses are maximum at the periphery, and penetration do occur from outside, So, therefore, cover concrete is most important, but that is poorest, durability is governed by cover concrete. So, one must put in a lot more effort on the cover concrete, all right. So, good concrete is only in the core. So, ingresses takes place through the cover concrete, stress and strains are maximum at the cover concrete, and cracking also first takes place at the cover concrete. Even if it takes place as inside, does not matter, but when it comes to the surface, it would actually cause more penetration of more harmful ingredients, and therefore, durability problem will be enhanced further. So, near surface, this is what governs the cover, governs the durability. Is there a way? Well, there is possibly some way, but at the moment this is inherent in concrete. So, you may have to keep water cement ratio somewhat higher, put a overlay maybe, we will see that of course. Tensile strength and elastic modulus of cover concrete is important, because this governs cracking, this governs strains from the stresses that is applied. Permeation quality at the surface, this is most important, and both are controlled by property of porosity of cover crate and through water cement ratio of cover crate. But we have no way to really control the water cement ratio of cover crate just like that. There is something which you can do, I will just come to that, but we can actually do what? We can improve the cover concrete by overlays, put a thick layer. This is your concrete, let us say, this is your concrete, this is your original concrete, put a cover layer, put a layer here. So, that is overlay. Coating, put a coating here, put just a coating. Pore blocking treatment by pore blocking treatment or pore liners, actually waterproofing treatment these are. I might have an waterproofing admixtures into the concrete. Also, I can put in some material which I can brush application I can do here, I can do brush application onto the concrete surface, I can do brush application onto the concrete surface, and this material penetrates inside. Some of them reacts with substrate, some of them reacts with the substrate to block the pore. Some might act in the at the boundary of the capillary, react and just get adsorbed there, react or get adsorbed there, and in the process they change the contact angle of water inside. Since most of the ingress is through water, it will not allow water to come in. So, this pore liners, pore blocking treatment, these are actually waterproofing treatment, and if water do not go in, then obviously durability will be enhanced. So, cover concrete can be improved by this sort of situation, but then at the moment of course, we do talk in terms of water cement ratio and cement control, but some of them could be costly. For example, overlays could be costly, coating could be costly, because you may have to repeat them over a period of time, as we have seen earlier, that you may have to there is a service life for this one also, and it may have to go on changing them from time to time. So, therefore, if you change them from time to time, there is a recurring cost involved, life cycle cost will increase. So, this could be there, but then one way is to use a control permeability foam liner. This is actually a material something like this, this, let us say this is a material, it has got as a pore liner, it is essentially a thin material put in onto the formwork. This is a thin material, this is the formwork, this is the form, this is the formwork, or let me write it like do it like this formwork. On that I put a liner, thin liner. Now, this liner is a porous material, it is a porous material, the porosity of course varies, So, it has got a filtering effect, and then there is a drainage. So, inner side it allows water to come in, but no solids, no cement particle can enter here, and its back side it has got a kind of a drainage, it can allow the water to come in and water can drain below, down below. So, when you are vibrating, the water tends to move this side, air tends to move this side. So, it will actually take out the air and water and allow it to drain out. So, there is a first phase, first is it is a thin material, it has got two layers actually, front layer, this is a filter layer. So, it is a filter, say polymeric composite material filter, and back layer is actually a porous layer. So, it has got the function to drain, function of drainage, this has got a function of filtering. So, A is here, B is here. So, cement particle or this material moves along this direction, water etc., water moves along this direction, but cement particles are blocked here. So, water moves along this direction, comes here and gets drained off. So, result is low water cement ratio at the surface, result is low water cement ratio at the surface, So, you see this is the lining material, So, when you vibrate, this is the lining material, this is your formwork, this is the lining material, and water and air will have a tendency to move, towards the outer periphery, and when you have this material, what happens is water cement ratio here reduces significantly. So, if your original water cement ratio was somewhere around 0.7, without the liner, with liner it might go even to 0.4, where here it is 0.5. This is a reinforcement bar. So, reinforcement bar is here, without the liner water cement ratio is very like this, with liner water cement ratio might vary like this, with liner water cement ratio might vary like this, with liner water cement ratio might vary in this manner, with liner it can vary like this. So, therefore, what we see is lower water cement ratio as the cover crate, denser cover crate, but and no bug holes, it gives you a fantastic finish, but unfortunately it is extremely costly, it is very costly and has not been popular at all because of its cost and also application difficulty, because you have to put it over the formwork, apply it over the formwork and fix it over using a tape. and since it's like by reducing, I mean you cannot demonstrate quantitatively how much will be the advantage at the moment other than qualitative advantage. So, this kind of system might work later on or maybe develop later on, but at the moment it is costly, it is not really used as much. So, this is what we have seen, how you can control the duration.